I want you to place all the 4 queens on the chessboard, so that way they don't cross out each other, right? You want to play them in such a way it cannot be captured. You know how the queen moves: horizontal, vertical, and diagonal. Your role is, as a team, I'm going to start placing 1 queen at a time. Okay? The goal is to place, we already talked about 8 queens problem. Here I'm just making you think. But when you do that, simply don't say where you're placing it. I want you to write down while you're doing it the steps. How are you solving the problem? So if there are three of you working on it, say, okay, let's play the queen in A11. I'm just calling it A11. Chess notation is different, okay? Morning Pragati. So you place the queen there. Say, okay, step 1, we place the queen there. Then what do you do next step? Okay. Now you say, okay, we went to the next row. Okay. We can't place it in A11. We can't place it in A22. I mean A21, A22, right? Then we place the queen in A2. Okay, because that meets the criteria. At some point you are going to get stuck. When you get stuck, you are backtracking. Okay, remember that is the philosophy of backtracking. So what backtracking you are doing, to which row you are backtracking, that is what I want you to write down in the steps. You understand the problem? So stand yourself, please. So, together in teams of 2 or 3, Pragati and Mandava if you are on, everyone is muted now. Okay, great. So, is there anyone who does not understand the problem? Your role is draw 4x4 matrix on your sheet of paper. Place a queen. Akkada queen ante mark pettukondi akkada Q ledu. Then you put another cell Q for queen. Then at some point you get stuck. Then you backtrack. So I want you to clear it up. Stone those papers for queen. And I gave time of 10 to 15 minutes because since you have to write the steps and steps also. Okay, faculty members, I assume you understand. Please guide the students and turn on your videos so that way I can see them. Time starts now. Ready, set, go. Advainda, Chaitanya, Jntuk Kakinada. You should be working in groups. I just gave a simple 4 queens problem. So that way you get a feel for backtracking. Make sure you write the steps. Because I'll pick one of you to show your steps to the class. Kaitalu unnaya to work on? If not, go get the computer paper. There should be some computer paper there, right? Turn on your videos. I can enjoy seeing the student solve the problem. Solve the problem. Okay. Okay.
We have inverse supports in place for managing the content.
There you go. Right?
But if we get any
Fair enough.
for some
Now I ask you to list the steps. So who has listed step number 1, step number 2, step number 3, step number 4? So who put the steps while doing it? Yeah, visually it takes only 10 seconds for me to put 4 queens on the board. The time that I gave was to list down the steps, your thought process. So who can give me that thought process there? Put that in the chat and then we can discuss that.
So when we go for expansion, we will obviously look for something high-end combination.
That's what I'm trying to get the students to think, right? Placing them is ridiculously simple. So if you whatever the steps are, how you do it, right? Now I'll give you an example. You started off, you said you place the queen in first row, third column. Okay? I don't think you'd have started off placing the queen there to begin with, right? Where would I have placed the queen to begin with?
Proposal and all the technical specs.
Let one student answer. Where would I have placed your queen to begin with? Logically speaking, you have an empty board. I know I cannot hear SVCW, but that student seems very animated. That's good. Right? She's telling the steps. I know that animation tells me that she's excited. Okay. Voice is not clear. Okay. Somebody is saying my voice is not clear. Then I have to again put it in the chat saying, can you hear me, right?
This is the advantage. So please, with the permission of our vice
Can everyone hear me?
Because I can't say, yes, we will use it.
Pragati cannot hear. It's not clear, they are saying. But what about others? Can you hear me?
If you want to give me 1 kg gold free of cost for Jntuk,
Yes, no, perhaps. Yes, there you go. Pragati, I think it could be a problem at your end. I think other colleges are able to hear me well. Oh, you are able to hear me now? Okay, that's good. Great. So, where do we put that first queen to begin with? Right? 99.99% of you. I don't want to be 100%. You would have placed the queen here, right? You agree or not agree? Agree, not agree? I hope you agree. Right? We cannot simply randomly pick some cell and put it, right? Step number 1, I say, okay, I'll go first row, first column. Okay? Now, we know queens cannot be in the same row, same column. Right? So, but in the backtracking, you do that, you go here, you try to place the queen here, in the next row. It is going to cause conflict, because this is all about conflicts, right? Conflict resolution. So you will not place it there. You will place it here. Just make everything black. There you go, right? You see a conflict there. So you will not place it there. And then you place it. Those are the steps that I wanted you to list. That's the reason I gave you 15 minutes. Okay. Because once you know how to write those steps, then you can solve an n by n queens problem easily. Okay. And you would solve a lot of other problems. Okay, so far so good, right? This goes here. Now when you come to step 3, you're placing the third queen. So by applying the same logic, you can't place it here, 3-1. You can't place it in 3-2. You can't place it in 3-3. You cannot place it in 3-4. Correct? Agree? So, at that point of time, the backtracking clicks. So the backtrack comes. So where do you go stuck? Nearest node from where you came. The nearest node is this one. Right? So you know that by placing this queen here, it is not going to help you. Correct? So then you have to possibly move this here. Right? That means you're taking the other patch. Can make progress, right? Can you place it here? Okay. Then when you do the other one, would that work? You can't now place the fourth queen. Now you have to backtrack here, right? When you backtrack here, then since we came from there, now you have to backtrack one more. Since this one was already placed, because of that these constraints came. Then you have to backtrack to the root of this one. The root of that is this cube. So this one now, then what do? Then you now, these things are not a winners. Now you move this Q to this Q. That is how you come up with the right designation. So that is what I wanted you to list. If you listed those steps like that, you came up with the solution, then you understand backtracking. If you simply visually did it because it is too simple to come up with a solution, you want to go back and do the steps at your convenience. Okay? Is there anyone who doesn't understand backtracking? Okay. So we will go more and more into that. Now, what I just did was, basically what we are doing to solve a backtracking problem is construct a tree, a state space tree, where all the nodes are partial solutions and edges show the choices in extending those partial solutions. Okay? And typically when we do these things in backtracking, we use a depth first search. And then when you encounter nodes which do not, which lead to a dead end, you prune them. So that way you don't have to explore those subtrees again when you know that those things lead to a dead end. And in your program there is a way to somehow denote the fact that that path leads to a dead end. Now for those who have not reviewed the slides yet, recall at the beginning of this lecture, last class, I showed you the tree structure, right? We reviewed this backtracking, how backtracking works, right? I just copy pasted that slide here again to refresh your memory. Okay? Now when we did that, it basically looks like a tree, right? This is nothing but a tree drawn left to right. Okay? And then we basically talked about what the terminology of the tree is. You have a root, you have internal nodes and leaf nodes. Okay? And backtracking can essentially be thought of as searching a tree for a particular goal. Now, continuing forward, this shows you the tree structure. How did we solve the 4 queens chess problem? If you had listed the steps, if you take those steps, translate them or transform them into a graph like this, you would see the steps visually like this. See how, if you take this is the empty board, you go to the left side, right? Left subtree, right subtree. So left subtree, you place the queen here. Second step, you keep going deep, right? Remember it depth. But the next 2 rows are empty because you cannot place the queen. Okay? So you backtrack and slowly build the tree like that. Okay? So outside of the class, take that 4x4 example. Without looking at this slide, try to draw the tree representation and compare that with the solution that is given here. So if you are able to come up with that, then you pretty much know how backtracking works. Okay? Questions, comments? Much easier backtracking than dynamic programming. Okay. What is the next class of problem that we solve using backtracking techniques? Remember, most of the backtracking techniques are essentially, we use them for like NP complete problems or for approximation of NP hard problems, where we are not looking for totally optimal solution. We are looking for suboptimal solution which is as close to perfection as possible. Better than a brute force approach, right? Okay. So the next example class of application is called the coloring problem. So what is the coloring problem? To get hands on, get your pencils out, sheet of paper out, okay? This is a much smaller problem, okay? And please don't put your answers for everyone. I'll repeat again. Please don't put your answers for everyone. I want students to think for a couple of minutes extra. Not every student thinks as fast as like an Einstein. 5 to 7 minute exercise, okay? Our students, Miranta, you all must be thinking, what is this today? The professor is making me do a lot of exercise in the class. I came to the class to take a nap and I'm making you work. That's what you must be thinking, right? Coloring problem that I want you to do. How many colors do you need to color this graph? Okay. And the constraint is no two adjacent vertices share the same color. What do you mean by adjacent? Adjacent means they are connected by an edge. Okay, ready, set, go. 5 to 7 minutes. Again, when you're doing those things, think through. Put your steps, write down your steps too. That will kind of help your brain, your neurons get fired up and they form those. You are welcome to put the answer in private mode for me, but not for everyone yet, okay? Okay, I do see SVCW working on it. Sentence, good morning, good to see you. You missed a few classes. Very dangerous to miss classes, okay? Unless you're all geniuses, right? You don't need lectures. The screen there, let me move it away. So how many colors do you need to color the graph? And no two adjacent vertices share the same color. A set, good morning. You can turn on your video if you can, if you have the bandwidth. I do see SVCW, I do see Jntuk. Again, SVCW, the instruction was simple, don't put anything to everyone. Chaitanya, are you still doing it? If so, if you have an answer, you can put it there. Jntuk Kakinada, if you're still doing it, you can, if you're done, you can put your answer there. So can other institutions if they are done finishing. The answer there, I got it, thank you. Thank you for putting it in private. Sentence Chirala, if you got an answer, you can put it in the chat. I'll give it 30 seconds more, then we'll keep moving on. Okay? Okay, so let's assume that I colored this one. So you start off with some letters, some kind of tie breaks based on alphabetical order. So we can start off with A. You can choose one color, let's say green. What are the primary colors that we have? GRE. I remember it based on the initials of my late professor G.R. Babu. Okay, G is for green, red is for, R is for red, E is for blue. That's how I remember my primary colors. So if you start off with A, green, then you go to between C and D, you break the tie break, follow C. Then you can use the other color B. Okay, blue, green and blue. Okay, so D, you have to use the third color, right? Green, blue, red. That's how you manipulate it and keep going. And somebody put the answer as chromatic number is 3. That is excellent. That is correct. Three is the 3 colors is what you need to color this graph. Okay. It also is known as a chromatic number, the minimum number of colors that you need to use to color a graph. Just to let you know, the coloring problem is the NP hard problem. Cannot be solved. Research for an NP for general classification of problems. Okay. Let me ask students a question. How many of you remember India map? Show hands. India map. Everyone knows India map? Can you draw an India map? How many of you can draw an India map? Show of hands. Come on, Mera Bharat Mahan hai. You should be able to say you can write, right? So, there you go. This is the Rajiv Gandhi. I don't know what the new Prime Minister says. I only remember Mera Bharat Mahan hai. Okay. Okay. So, how many colors do you think the map has? 2, 3, 4, 5, 6, 10. How many states are there in India right now? Is it like 35? 35, 40, 28, 20, I don't remember how many states. When I was growing up, it was I think 22 or 23. But in these 30 years, it has split, right? So, anyone remembers how many colors are there? You can put it in the chat. Okay. What is the, if I have 35 states, let me, right? How many maximum colors we can use? Order of n, right? If I give you the same question in an exam, you will be nervous, right? I know my upper limit, 35, because the 35 states, I choose each one distinct color, right? But obviously we don't need 35. What is the minimum number of colors that we can use to color the entire map? So that way no two adjacent states have the same color. That's the coloring problem. Think about it. 29 states and 7 union territories. Union territories are islands, right? I wonder whether an island is considered, if you graph model an island, is it considered adjacent to like Calcutta or something like that? If I say Andaman Nicobar, I don't know. The sea is there. Maybe we can consider them as adjacent and still try to solve the coloring problem. So this coloring problem became very famous because everyone wanted to color a map. It's a very fascinating math problem actually. Okay. And then it has been proven that there is a theorem called four-color theorem, okay? You need no more than 4 colors. Okay? Now, once you start coloring, how do you know, right? This is another case where you are basically applying backtracking technique. There is no clear choice because we don't know the full data. We don't have the full data in front of us. Okay? You make some choice, you move forward, you start coloring from country, state 1, state 2 and so on. Whenever you get stuck, you backtrack. Okay? Get stuck, backtrack, get stuck, backtrack. Now if you have covered all the leaf nodes and you still did not solve the problem, that means the problem cannot be solved. But the fundamental algorithm for coloring still remains the same. Mandava, I am muting you, I think. So static is coming. Okay. So that is the example of coloring. Let me see what I have here. Second. So in the 1920s or 30s, I don't, or maybe close to 1950, some mathematics right, and where when you have two countries a common border, they will always have different colors. Okay. Again, as I told you, it's not an easy problem to solve. It's actually an easy hard problem to solve. So the next set of slides are there to just tell you how an algorithm would look like. They are not there to teach you in the class that this algorithm works. Okay? Remember, I keep putting some algorithms every now and then, right? I tell you to go review those algorithms, put some test data, run through the algorithm, make sure it is working, right? That's how you increase your created a couple of arrays. One is a single element array for colors, because we are talking about a coloring problem, right? It says what is the country color I. Each I is an index of the ith country. Okay, you have some cheat sheet. You say I equal to 0 is India, I equal to 1 is Pakistan, like that, right? And then you have an array of adjacent countries, because you remember we talked about adjacency matrices and all that some time ago. Give me a second. 1 second. Hey Phil, stop. Stop. Okay. 3 equal to 8 means the third country adjacent to country 5. Okay? Meaning that country 5 has some adjacencies, adjacent countries. And then you can see the value 8 there. Okay? Okay. And then the country that is adjacent to the country 5 is country 8. So how do you create a map? Typically this is, you have some kind of an array structure of all the colors. Okay? You're creating a map first, you initialize the data, right? So the author has to set the initial values for the colors, right? Standard enumeration, right? This looks like an enumerated list of values to me. And you are initializing the array map of colors to begin with nothing. Okay? And then you have the main. Every piece of code should have a main. So you are creating the map. Okay? And then you can see how the backtracking algorithm is going to be applied. So there's a bunch of code there. Again, as I said, you have to convince yourself, take some test data, take a small set of, call it like ABCD. Actually draw the picture, some of the pictures that I showed you in the past few slides. Okay? And then finally you print the results. Okay? So what we did, what that piece of code essentially did is the following. Okay, I recapped it for you in English, then go back and map it to the algorithm that I've given there. Okay, so you go through all the countries recursively, starting with country 0. Remember, all countries have been given some indices, right? 1, 2, 3, 4, 5, and so on. Or since we are computer scientists, we start with 0. So we have to decide at each country. Now, so that means you are comparing the color of each of those countries, right? You already have a colors palette, so you compare each of the countries from the color palette, and if it is there, then you remove that. That's how you track it. Pretty standard piece of code there, right? If you cannot find a legal color to color, then you stop because it's failure. You need to have one of the colors for that country, right? Okay. Now, if you find a color, use it. And then you go to the next country because of recursive code. Okay. If you have colored all the countries, meaning you said for I equal to 1 to 80, if you have a for loop, that means there are 80 countries, right? You're done. So the algorithm itself is ridiculously simple, right? Compared to the dynamic programming algorithm that we have seen. So that is the essence of backtracking applied to coloring problem. Okay, let me stop here for a second. Questions, comment. Now the entire coloring problem, before I get into sum of subsets, as I told you, it's an NP-hard problem. It's still an active area of research. Enormous amount of research went into coming up with and so on. You can just Google up something on coloring complexity. You'll get all kinds of time complexity measures on that. I don't know if those are the kind of things that you'll be asked in a final exam. But if you do, once I see some practice papers, I'll be happy to tell you some of the standard time complexities for coloring problem. So you can just memorize or something like that and go to it, right? Okay. So we covered Queen's problem. We covered coloring problem. Okay. Now we are going to get into sum of subsets. Section I'm giving you an exercise, right? We'll do it as a group here, okay? Instead of giving you 5-10 minutes, we'll do it as a group here, okay? What is sum of subsets? Oh, sorry. Let me pause there before I go to sum of subsets. Where do we apply the coloring problem in real life? Why is it a big deal, right? You would notice that the coloring problem is actually almost like a graph decision problem, right? If you convert them to graph, whenever you have graph, you have two things that you solve when you have graphs. Optimization problem, meaning, like for example, shortest path. That's a tree, right? We're optimizing the distance. Now you can equate the distance on a graph to cost, resource cost, right? So you use these concepts to solve applications like scheduling. Okay? When you're scheduling jobs, remember we did the capital budget problem. That is an optimization problem too. So you basically use these coloring applications to solve scheduling, optimization. There's some search algorithms. So reservations, when you talk about they use this approach. I mean, I assume they use this approach. And your own professors, your own JNTU, when they are scheduling classes for all of you, they are essentially using the coloring problem and the backtracking things, the algorithm, the backtracking techniques to come up with your schedule. Chakravarti garu correct ga cheppana adi mee scheduling lo backtracking untundi kada meeku. Any other faculty member can help me there too. Whenever you do scheduling, there is some backtracking involved in the scheduling. Scheduling of courses, scheduling of professors, and scheduling of classrooms. Okay?
Scheduling the timetable also.
Timetable, there you go. Thank you for telling me that. Timetable for the classes, right?
Yeah, assigning subjects, assigning timetable for all the faculty members also we use backtracking, most of them.
Vaccine, yeah. It's such a practical application, but the backtracking concept is so simple, right? So that's why I wanted students to get some practice too. That's good. Thank you. Okay, let's talk about sum of subset. What a subset sum problem is, right? Basically, you have a group of numbers, right? You are doing a subset sum problem to find a subset of elements that are selected from a given set of numbers whose sum adds up to a given number k. So I gave you an example here. Okay. You have the following numbers 1, 3, 7, 15, 8, 10. I want you to select the subset that add up to 19. Okay. So let's do that. So what are the numbers that add up to 19? Let's create some. Please tell me some numbers here. Goal is to have 19. Edit text. Okay, who wants to go first? It's 19. That is what we are trying to solve. Okay. So if I pick 1, 3, that is 4, right? 7, that is 11, and then I can pick 8. That's 19. Got it? Okay. Control C, Control V. Okay. Is there any other way of doing it? If I pick one more. Or I can say 1, 8, 10. That's another subset, right? Which adds up to 19. It we used to, I remember as growing up as a math kid, I always loved math, right? So we used to solve puzzles like this. So the algorithm, we use a backtracking algorithm to identify the sum of subsets. If you notice carefully, in capacity building, we kind of use that. Okay, go back and review that. You will get some of these concepts. can always do an exhaustive search for a subset sum, because all kinds of permutations and combinations, right? Agree? And then if there are n numbers, you know that if there are n numbers, 2 raised to n is the total the space, right? If I have 3 numbers, 2 raised to 3 is 8. Remember binary logic, right? Of course, if you use zeros and ones, then it's 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, blah, 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 right? You'll get 8 numbers. That's what this is, 2 raised to n. Okay? So, depending on how many numbers are given. Instead of doing that exhaustive search, we can apply backtracking, okay, and then apply some of the principles that we have learned. With the same principles all over again to solve this problem too. Okay. There are different ways of doing it. I'm showing you one example here. If you are assuming, let me see if I can explain this graph. I had difficulty understanding it myself first time after a long time when I saw it, but I'll try to explain. If I screw up, don't worry, because there's another nice simpler example than that, okay? But I'll give it my best. There are 4 elements, okay? W1 to W4, okay? So when you have 4 elements, you're starting at the root node. Root is your starting step, right? What are we doing? It's a subset, right? Sum of subsets. So you have a choice of selecting any of those 4 numbers, right? Either W1, W2, W3, W4. So you build your tree, first level tree, based on those 4 choices. Okay. Now once you make a choice, I'm now going on W1 subtree side. You have since you did W1, you have the choices of W2, W3 and W4. Remember, it is the tree is in a backtracking thing. You go depth first. You did the 1, then you go to 2, 3, 4. That leads you to 6, 7, 8. Okay, you're with me so far? That's SVC review correctly. You're right. That's what I'm coming to now. Now you finish W1, W2. So when you're at 6, what are the choices that you get? Since you finish 1, 2, you go to 3 and 4. Then you are at 12, 13, and since you did W3, you do W4 here. Okay? Now after you backtrack all the way up to W1 is done, when you go to the next branch, W2, since you are at W2, the following numbers are 3 and 4. That's why you see there's 2 branches there. And once you do W3, following 3 to W3 to 9, the next number remaining is W4. The right subtree of go to the third one, W3. Since W1, W2, W3 are done, you just do one level deep for W4, and then last one is W4. Okay. Now if you add up these values, depending on what is the sum subtotal that you are doing, somebody said 1, 3 and 15. If you add up, it comes to 19. So 1, 3 and 15. Okay. So you go 1, 3 and 15 like this. Where is 1, 3 and 15 and Nikada? Do you get it right? unless I correlated the numbers here. Let me check. 1, 3 and 15. There you go. Perfect. So 1, 3, 4 plus 15, 19. That is how you come up with the optimized solution. Okay. So the trick here for backtracking is essentially to draw a tree. It's converted, it is basically transformed into a tree problem. And once you have a tree or graph, in tree is a graph too, right? So you can then apply the graph theoretical principles to solve it. Okay, that was some heavy duty picture. Candidate element, right? So it shows the explanation. Root node contains 4 children because you have every element of the set. Okay. And the next level subtrees correspond to the subset that include the parent node. This is the reason why once you have the parent node, you have to go forward, exclude that, and then go to the next set of nodes. Okay. And then at every stage of the branch, you have a couple of decisions to make, right? That's the reason why you have it represents the tuple element to be considered. When you consider the tuple element, what do you do when you add it? If it goes the moment it goes exceeds 19, that branch is a dead end. You have to backtrack. Okay. Okay, that is what that is. That's what this says. As we go down along the depth of the tree, we keep adding elements, and if the added sum is satisfying the constraint, we'll continue to generate further child nodes. Okay. Now when the constraints are not met, we stop further generation of subtrees and backtrack to the previous node to explore the nodes not yet explored. Okay, questions, comments? It was not a binary tree, right? So I picked up another example. In this case, we are going to draw a binary tree. Okay, and the state space that we have here is 3, 5, 6 and 7, and we are looking for 15, the value 15. Okay, so how is this tree drawn? Let's look at that. Another big nice slider, looks colorful. I will try to explain faculty members. Anybody wants to help me explain this picture, please? That way I can get some rest for my voice. Chakravarti garu, you want to volunteer, or SVCW faculty member, you want to volunteer to explain this slide? That way students get to listen to everyone. No volunteers. I thought we have an enthusiastic group of Chakravarti garu, you volunteer just now, or SVCW. I wanted we can collectively explain it to students, a couple of faculty members together. See students, it's not just you who I make you participate, right? Even faculty members participate. A lot of faculty members who enthusiastically give solutions in the chat. Okay, Chakravarti, so our mic is not connected to web, okay? No problem. Some colleges, they Vijayanagaram, do you have mic on? If there is a faculty member there today, I don't know. Any college, anyone can do it. And Chakravarti garu is keeping quiet because he wanted to give others a chance. How about I tell you? Is there a student who can explain that? Just looking at the picture, looking at that, what is happening there? Any student who can explain that, I'll give them a lunch coupon in a 5-star hotel. Kakinadlo, I'm sure there are some good star hotels. Okay, so it's actually pretty simple. When you see it, it looks complicated. But if you really look at it, what they are doing here is right. And they did a binary because they say if I take the number 3, let's take just number 3 here, right? Okay. So if you take number 3, you come here, first number, right? You have to take the first number. So you go from 0 to 3 here. Do you want me to put it in a slight bigger mode? Better? Okay. Let's look at it this way. And I can trust my voice a little bit, but it's okay. I'll handle it. If I screw up, somebody can jump in and put it in the chat. So what is the binary? We have 3, 5, 6, 7. Okay, I'm going to take the value 3. So I go from 0 to 3. Why did I put 3 here? Whatever value I took, that value is displayed in that node. You're with me so far? Students, show of hands. I can see SVCW. Do you understand that first part? Raise your hands if you understand that. Okay, I see SVCW raising hands. What about Chaitanya? Do you understand that? Chaitanya, did you raise your hands? Otherwise you are lost. You may as well take a nap at that point of time. Okay? So with 3, so all we are saying is let's consider the first number. So I took the 3. I put the value 3 there. Now after 3 is done, I have a choice. It's a binary tree, remember? The next number is I have to follow with 5 or without 5. Okay? So let's say with 5. With 5, that means 3 plus 5 becomes 8. So I put 8. Once I finished 5, what is the next branch? Remember, we keep going deep, right? Depth first. Okay, next number in the sequence is 6. So here you have 2 branches. With 6, without 6. They are ordered in increasing sequence. It helps if they are ordered. Okay? You can solve it without ordered also, but it gets more complicated. Okay? So now we should add 7. What happens? 14 plus 7 is greater than 15. You reached a dead end. So you stop there. And once you stop there, from 14, what do you have to do? You have to backtrack. Where do you backtrack to? The above one, 8. So what is the next branch you take after 8? Without 6, right? So without 6 you come here. It's a zero weight problem. You come here to 8. Right? So you add 7, you get 15. Okay? So you do with 7, without 7. So if you do without 7, then you add 8. It's all 8, right? Without 7 means 8. 8 is less than 15. So it's not a solution because there are no numbers after that. Right? After 7 there are no numbers. So you exhausted the set. Okay? Now you backtrack from here to here, 8. From there you backtrack to 3. You follow the branch without 5. Build the same tree again here like that. Okay? Now you go backtrack to the top. The reason that's one way. But on the other hand, if there are other solutions where you don't have to go that deep to arrive at 15, then maybe that is better, right? Because it's less traversal. So going back here, you then say, okay, 3. Then we go the other side, it is without 3, that's 0. Then you consider it with 5. With 5, without 5. You follow the 5 with 6, without 6. Like that you build the tree. Okay? Now, this is a very legitimate question in a final exam where I can give you the same set and say, show me a tree, how the tree structure looks like. In a an above average excellent student will probably take 10 to 15 minutes. And the rest forever. If you don't get it in the first 15-20 minutes in a test, you may as well give up on that, right? And move on to the next question. Okay. So this is how you solve. If I give you a final exam question saying draw the tree and show me the path which arrives at that sum, that becomes a subset sum problem. Okay. I can also, what I do here is I can also give a question such as Bihar, right? You saw that people who climb the walls in Bihar in colleges and they turn in the answer sheets for people to fill out, right? Cheat sheets, mass cheating, right? In this case, here what I do, I give a general problem. So that way that cheating will not happen. If I simply say, demonstrate your understanding of this with your own example, then almost all students would have their own separate examples. Okay? So you should be prepared to answer either way. Okay, I survived that part. What I explained, but you can see as you are following it, if you see the last bullet here, right, as long as the sum is, you want the sum not to be too large, meaning you should not go to above the value that you are looking for. Similarly, it should not be too small. That is what this entire theory says, what I explained there. Questions, comments? Another interesting thing, beautiful thing, I tell you, this is such a nice example. That's pretty much it. That completes the this chapter actually. So let me spend some time here. Okay, just take a 2-minute break. I have to go get some water. I'm feeling very thirsty after all that explanation. 2-minute stretch break. You can stand up, do some yoga. Just take 2 minutes and we'll be back. Okay? 2-minute break. So I do see some students taking the break. I think they are very appreciative, I guess. I usually give breaks every 1 hour in my classes here. This is another class of problems where we can use backtracking techniques. We talked about Hamiltonian cycles in a couple of classes ago. I don't remember which one. Who remembers what a Hamiltonian cycle is? Can somebody put what a Hamiltonian cycle is in the chat, since some of you do not have a mic? We covered that in the context of something. Anyone remembers that? You can put it in the chat. I'm assuming you can hear me, right? Faculty members are welcome to put that too. Students don't remember. Is everybody exhausted or what? Nobody is responding. Remember when we talked about all this shortest path problem, traveling salesman problem and all that stuff? We said that if you have a group of cities, what is the best way to go cover each and every okay, once and come back to the source. Right? We talked about that. And then if you don't come back to the source, then we talk about a path, Hamiltonian path. Okay, that is a classic traveling salesman, right? They start in one city, they want to go in an optimized way. If you go back to a few weeks ago slide, we said that I gave you one nice algorithm where we said these are all NP hard problems. They cannot be solved in polynomial time. They cannot even be solved. They basically cannot be solved in polynomial time, right? So forget the name, where we do it twice. Each node is visited twice, and then over a period of time, the intelligence as to what are the shortcuts is accumulated, and then you start pruning some of the paths. So eventually you'll get to as close to a Hamiltonian path, not totally optimal, but almost optimal. Okay. Go back and look at those slides, you will find those things there. So that is another case where we are actually applying some of these backtracking techniques. Okay. Now what do we see here? We make vertex A the root of the state space tree. So we want to remember backtracking means tree. Okay, let's do it live for the fun of it, okay? That way you will appreciate it more, right? So how do I do it live? I need to create a slide, I guess. Or I can try to write it here, maybe. I'll try to write it on the same slide. So backtracking is, we are going to break the tie. Come on, Pratap. Be efficient. Okay. So we start with A, right? Then where do we go from A? Somebody put it in chat. Don't give the solution yet. According to backtracking, what do we do? From A, we can choose. Then from B, you have branches C and F, right? So then we proceed to C, alphabetical. Now from C, we say you have a choice of D and E, so you choose D. Then from D, you go to E, because that is the next node, right? Now you're stuck. You can't go back, correct? So now you have to backtrack from E to D. Now when you backtrack from E to D, from D also, where can you backtrack to? If I go to F, from F I go to E. Correct? And E, I have C and D. I choose the alphabetically, C wins over D, so I go to C. From C, there is one path to D, right? Once I come to D, E has already been visited, so I go to A. I think somebody answered that A, B, F, E, C, C, D, A, C, D, A. Right? That is a Hamiltonian circuit. Is there any student who Okay, so let me see in the chat. Did somebody did they come up with some other answer to? Where did my chat window go? For some reason I can't see my chat window. I think I buried it deep somewhere. Ah, there it is. Somebody said we got only 4 solutions. Somebody said BCD, A, C, B, F, E, D, A, B, A, C, yeah, correct, A, C, B. Did I get the solution right? Here in the chat window. Somebody got 4 solutions. So who said that SVCW? Okay. ABF ECDA, ACB, F, EDA AC. Okay, now that is true, you can do that, but then if I put a restriction saying that when you have alphabet choices, the lower alphabet wins. The reason I put that constraint was, think of these edges as costs, right? Because it costs a certain cost, could be in terms of time. Have multiple solutions. Okay. What do I have here? I have the pictorial graph. Remember, today we saw a lot of trees, right? You can see how the tree is built. A, B, C. Remember, we came here. All these things, when you backtrack, you can see that dead ends. And then you go A, B, F, E, C, D, A. That is the solution. Okay. Now I want you to become don't say that to create those exams, but that's just my opinion. Okay. So I want to summarize this chapter. Okay, by giving some general remarks. So where do we apply this? We apply this typically, these are combinatorial problems, right? Combinatorial means basically they explode. The kind of thing that you have to analyze is a humongous data set, basically. And then there are no efficient algorithms, because to find exact solutions, if you have infinite come up with techniques such as backtracking, where we hope to resolve the search time. Okay, that is why we try to use backtracking. Okay. Now notice one thing here. When we did the backtracking, we didn't quite eliminate any elements of the problem state space. Okay, we might still end up generating all the elements. The only saving grace for backtracking is at least we know what we are doing, because it's a very specific technique, right? We are not randomly trying to solve a problem. It's a very systematic way of solving a problem. That is the reason why they are so valuable in whatever we do. Faculty members, would you like to add something to this chapter? From all the, I know most of you teach this class. Anything else that you would like to add on this particular Hamiltonian circuit or all the other topics that we covered in this chapter? Students, do you have any questions? No questions, okay. Questions at the moment, but what you should ask. I may answer, or some other faculty member may answer, or we may not know the answer. The next week's topic . Do you see my screen? Okay. So, next week's topic, the last unit is branch and bound. Okay. I know we have about 10 minutes, but I'm not going to go into that. I just wanted to give you a quick introduction. What do we mean by branch and bound algorithms, right? Okay. And then what we basically do here is, right, you're always, when you're building the tree, right, you compute a bound and the value of the objective function, right? We'll see what those bounds are. Okay, there are some classic problems. And then once we know what the bound is, bound means condition, basically nothing but a constraint, right? Let's say I say, hey, I want to choose people for these jobs, and each person costs this much to do the job 1, job 2, job 3, and so on. I want to hire the resources example that I just gave, and I know what my minimum bound is. It cannot exceed more than $100 if I say that. Then I use that criteria to start pruning out, meaning eliminating some branches of the tree because the cost exceeds that. That's why we call it, as you're branching, you're also evaluating against a bound. Okay? So that is the branch and bound problem. Okay? Now, what are the similarities and differences between branch and bound and the other standard one? Is similarities, they both use the same state. If you look at the backtracking algorithm, I kept on saying it's a depth first search tree, DFS, right? So we always did a depth first traversal of the tree. 1 second please. I have to close my door. Now my wife is happy, she had to close the door so that way she doesn't hear me, right? It's so funny, when I began dating my wife, I don't know if I told you this story. Go there to teach from 6 to 8, class extends till 9. So since from those days my wife intensely dislikes me becoming a professor or a teacher. But what to do? My first love is teaching, right? So I put up with all this to enjoy my teaching. Just an inside secret that I'm sharing with you. Okay. And I'm sharing because my wife cannot hear now, right? My door is closed. Okay, going back to this one. The difference really is, in the backtracking, we always use a depth first search. We went all the way from the top, all the way to the leaf. Left. So this is the basic idea. Okay, you set up a bounding function. If you compute it, we'll see some examples. Okay, if it is within the bounds, you continue. Okay, if the bound is better than the value of the best solution so far, go beyond the node. Okay, Non-promising, meaning it has exceeded the bound, then you prune, meaning you don't follow that path, you come out. Okay? So I will stop there. For students who came late, you missed my first two quotes. Once I put it in the community, this slide, you can take a look at that. Okay. I really like this slide, this particular quote. I thought I should show it to you. If you are not willing to learn, no one can help you. Even God cannot help you. My dad's famous quote was, if you're not willing to learn, even God cannot help you. Okay. If you believe in God. If you are determined to learn, no one can stop you. Very powerful. Think about it. So what it basically means is you should show real enthusiasm to learn anything. Okay? It's really not the teacher. It's I will hang out as always to answer any questions. For those of you who have come a little bit later, let me put something here for you. What the next set of action items are for us. Layout, bullet points. Okay, next. So we have on 2nd, not 2nd, today is what, 29th, right? Oh, for you it's 1st. Okay. So Monday, Tuesday, Thursday. So 3rd, 3rd, third, 8th మీకు time, 8th, yeah, I think so. 8th and 10th, okay. Then we'll do 15th and 17th. So 15th and 17th, review all units. Okay. Now if Chakravarti Garu can arrange that extra class during the week of 14th, reviewing from unit 1 onwards, beginning now. Okay, don't wait till the 17th. Beginning now, start reviewing from unit 1. I put a lot of material for you there. Review them, and then as you are reviewing them, you will get questions. Okay, if you don't, that means you are not doing a good job of reviewing. Now as you review, as you get questions, post those questions in the community so that we all can answer. Okay?
Sir,
to all of them, make sure which Saturday works for you. I can also do on March, if you want to do it like March 20th, which is March 9th, which is a Saturday, I can do it.
yes, sir.
Okay, any Saturday, you just let me know.
Yes, sir.
And then I will also check on my side. I just have to check with my daughter because She has speech and debate tournaments on Saturdays.
Sir, you
And,
have two options, either on 12th or 19th.
12th or 19th. Okay. Why don't you? Okay. What about other colleges? Would they be okay on 12th or 19th?
Maybe 12th is second Saturday.
Questions in the community. So that way all of us can answer. They don't have to wait for me or you. Anyone can answer those questions, right?
Right.
That is the power of MOOCs. Okay? Great. Thank you all. If you have any other questions, please shoot me an email as always. Whichever way you want to call me, you can call me too. Okay?